No, no. Okay, let's get started. Can you hear me? Okay. Uh, today we're going to talk about big data analytics, optimization, and randomization. And this is a joint work with my colleague Qihang and Dr. Rong. So due to some schedule issue, Dr. Rong will not present today. So today, me and Qihang will talk about this. So this is the URL of our slides. So if you haven't downloaded the most recent version, you can download following the link. Okay, some claims before we start. So first, this tutorial is not an exhaustive literature survey. We try to include the most recent and most advanced algorithms, techniques for solving big data. And also, it's not a survey about different machine learning and data mining algorithms. Instead, we focus on how to efficiently solve machine learning and data mining. Yes? So the link is available following the link on the KDD tutorial website. Instead, we are focused on how to efficiently solve machine learning and data mining. In particular, they can be formulated as optimization problems for big data. Okay, so this tutorial is divided into 3 parts. In the first part, I will talk about some basics. I will introduce you the problem, give you the motivation, and talk about some challenges. And in the second part, my colleague Qihang will talk about the optimization. In the third part, I will talk about randomization approaches. Okay, first some introduction. So here I show you the general 3 steps for machine learning and data mining. The first step is collecting the data, right? So without any data, you can do nothing. The second step is usually build up a model, and the model will depend on what type of task that you are interested in. It could be classification, could be regression, could be ranking, could be clustering. The last step usually end up with optimization step. So optimization is used to find the best parameter that defines the model. Okay? So after finding the best parameter of the model, we can apply the model to make predictions on the future data, on the new data. And nowadays, we have big data challenge. Right? So huge amount of data are generated every day. And the big data refers not only to the size, to the number of training examples, but also the high dimension, a large number of features, right? And in the meantime, when we have big data, we want to increase our model, right? To have a better model. So we want to increase the size of the model. So we have the big model. And here I show you the big neural network that was used to train train for ImageNet classification, 1,000 classification problems. And this model contains about 60 million parameters. So it's really a huge model. So how to train this huge model becomes very difficult problem. So this big data and big model poses great challenges because most the machine learning problems can be formulated as optimization problem. So to give you some examples, so here I show you the rich regression problem. So we are given a bunch of training data. So xi is represents the feature vector of the ith example. It's a d-dimensional vector. And y is a target variable. And here we are interested in learning a linear model W, okay, which make predictions by the inner product between W and the feature vector. So here, in order to find the best parameter W, we minimize this objective, so which consists of two parts. The first part measures the loss of the model on the training data. So here, this is the least squares error. Okay, so this is the average over the training data. The second part of the objective function contains is a regularization term. Here is the standard Euclidean non-square regularization. And the purpose of introducing this regularization is to avoid overfitting. And classification problem can be formulated similarly, except that the loss function is defined differently. So here, if we are interested in the binary classification, the label y is positive 1 or negative 1. And here the loss function, so this is a loss function which defined over the prediction times the label y. And here the loss function could be Hengel loss or squared Hengel loss if we take the square. These loss are used in the famous support vector machine method. And also you can use logistic loss for the logistic regression. And also here, you can replace the Euclidean non-square with L1 non-regularization for some feature selection task, for example, because here the L1 regularization can enforce the sparsity in the optimal parameter W. Okay, and in all these formulations, the lambda here is a regularization parameter that controls the balance between the empirical error and also the regularization. So here you can also use some other regularizations. For example, this is an elastic net, so which replace the L1 norm with a combination of L1 norm and Euclidean norm square, which is more robust than the L1 regularization in some cases. And in some cases, we are interested not only learning a vector, but here we want to learn a collection of models. So, for example, in multitask, multi-class learning, we are interested in learning a matrix, which is actually each column corresponds to a model for one task for one class. Okay? And the objective function is similar, which contains two parts: the empirical loss and the regularization. So here you can impose regularization on the matrix using Frobenius norm, using Euclidean nuclear norm, and other norms. Okay, so in this tutorial, we are going to focus on this general formulation. We have this objective, which is one part is empirical loss, another part is regularization. So here, I absorb the regularization parameter lambda into this R function. And here, we assume both the loss function and the regularization are convex functions. So the problem is a convex optimization problem. And here we focus on this vector for the parameter. And extensions to matrix cases are possible and sometimes are even straightforward. And extensions to kernel methods can be achieved by combining the randomized approach that I will talk about in the third part. And extensions to the non-convex problems, for example, deep learning, deep neural networks are in progress. And some methods have been already used in training deep learning. For example, stochastic gradient descent with momentum, which Qihang will talk about more later. Okay, so that is one side, which is the machine learning are usually formulated as optimization problem. And here I want to discuss another factor, which is a data matrix. Because many, I think almost all machine learning and data mining tasks are formulated based on some kind of data matrices. So here, the first most popular data matrix is probably this instance feature matrix. So so you collect a bunch of training data. You represent each example by a number of features. Okay, so you can organize this into a vector and put the feature vector in one row of the data matrix. Right, so here, this X is the data matrix which contains n rows correspond to n training examples, and D here is correspond to the number of features. Right. So here I visualize the data for the iris data for classifying the iris flower into three species. You can see actually the input data matrix can capture the pattern of the three classes. So and also we can organize the in supervised learning. Each training examples is also associated with some label or target variable. So here we can also organize into a vector. So here we call the output vector y. So the second data matrix that we sometimes use is actually captures some kind of relationship between training examples. So for example, the similarity matrix, the kernel matrix used in kernel method. So here this picture visualizes the kernel matrix of the iris data, and you can clearly see the three block structure for the three classes of examples. And also some machine learning tasks are formulated based on the kernel matrix. For example, kernel method, kernel SVM, and also kernel clustering method. So the last type of data matrix that we usually encounter that captures the relationship between features. For example, the covariance matrix. For example, the distance metric matrix. So there is a type of machine learning problem called distance metric learning problem, which is actually to learn such a matrix which captures the kind of relationship between features. And the covariance matrix has been used in principal component analysis, where you want to compute the top k singular value decomposition of the covariance matrix, right? So those are three data matrices that which we usually use for machine learning and data mining tasks. So from that, we can actually start understanding why learning from big data is very challenging. So if you have a huge number of examples, huge number of features, the data matrix is usually very large, right? So sometimes the memory cost is very high, and sometimes you cannot even load the data into the memory, right? So if the data training data is too big, you probably want to distribute the data over many machines, right? So in this case, you want to design some kind of distributed optimization algorithms to coordinate these multiple machines. And in this case, it will increase the communication cost between the machines. And also the big data, also increase the per iteration cost and also the iteration complexities that will Qihang talk more later in the optimization part. So what we are going to present today is actually the algorithms and techniques that try to reduce this cost here, okay, for the big data. Okay, some notations and definitions. So here we use this notation x belongs to this to indicate that x is a d-dimensional vector. And for d-dimensional vector, we can define, we can compute some norm. For example, we can compute the standard Euclidean norm, which is defined here. We can generalize this into a more general norm, for example, LP norm. Right? And this includes, for example, L2 norm, which is a Euclidean norm, and also the L1 norm, which encourages the sparsity in the model, and also L infinity norm. So for matrix here, later on, we probably mention several kind of decompositions, factorizations. The first is the singular value decomposition. So we decompose X into two orthonormal matrices and a diagonal matrix with non-negative entries. So here, we use this notation to denote the top k approximation, which will only retain the top k singular values and their corresponding singular vectors. So given this singular value decomposition, we can define this so-called pseudo-inverse of a matrix X So pseudo inverse here is computed by V sigma inverse times U transpose. Okay. And another factorization that I will mention later is this QR factorization. So which factorize the matrix X into orthonormal matrix and upper triangular matrix R. So for matrix, we can also define a norm, for example, the Frobenius norm, which is actually an extension of the Euclidean norm to the matrix case. And we can also define the spectral norm, which is induced by a Euclidean norm on the vector. And if we know the singular values, the spectral norm is the maximum singular value. Okay, so since we are interested in the convex optimization, so I want to talk a little about convex optimization. So here the problem, we minimize our objective function subject to that the X is in some kind of domain. So here we require both the domain and the objective function are convex. So for a domain which is a convex means that if you take any 2 points, X, Y, that in the domain, so if you draw a line segment between the 2 points, that should be also in the domain. Okay? And for a function, for convex function, they kind of different definitions. So if we use the function value to define the convex function, so you can take two value X, Y, okay? And you can compute a convex combination, which is alpha X plus 1 minus alpha times Y. And for that point, you compute the function value. So for convex function, it always satisfies this inequality. So the function value of the convex combination is always less equal than the convex combination between of these two function values. If the function is differentiable, if you can compute the gradients, you can also define the convex function using this inequality. So here at any point y, okay, you compute the gradient, you construct a linear function, which is a tangent line here. And this is the linear function here, which is fy plus the gradient transpose x times y. Okay? So a convex function must satisfy this inequality. So the fx, the original function, should be always above this linear line. Okay? So a good thing about convex optimization is that the local optimum is the global optimum. So if in the definition of convex function, we make it a little bit stronger. So instead of using this linear lower bounds, we have this quadratic lower bounds. So we add an extra quadratic term here. So make this lower bound to be a quadratic function. So if a function satisfies this inequality, which is said to be a strongly convex function, and here the parameter is strongly convexity parameter. And the good thing about the strongly convex function is that the global optimum is unique. So a function could be also non-smooth and a smooth. So here, for non-smooth function, at some points, the gradient may not be defined. But we still want to impose some kind of condition on the non-smooth function. So here, this is the Lipschitz continuous condition. So Lipschitz continuous function means that if you vary the point a little bit, so if you vary x a little bit, the function values will not change too much. So the difference between the function values will be bounded by a constant times the distance between the 2 points. Okay? So as I said, for non-smooth function, the gradient may not be defined. For example, this absolute loss at this point at 0. Okay? So the gradient is not defined. But here we want to define another kind of similar thing, which is called subgradient. Okay? So subgradient here at a point y refers to a vector, any vector that satisfies this inequality. So which is the inequality we define a convex function, right? So actually you can see at some points, the subgradient, there could be many subgradients. For example, at this point, there could be many subgradients can be defined, okay? So a better function than non-smooth function is the smooth function. So a smooth function is whose gradient, so we can always compute the gradient of a smooth function. And the gradient is Lipschitz continuous. So if you vary the point a little bit, the gradient will not change too much. So the difference between 2 points of the gradients will be bounded by a constant times the distance between the 2 points. A good thing about the smooth function is that you can always construct a quadratic upper bound, so which is a very important property, and that has been used a lot in optimization. And here the G is called Lipschitz constant, the L is called the smoothness constant. Okay, so what is next? Okay, so in the second part, Qihang will talk about optimization. So basically, he will talk about stochastic optimization and distributed optimization for solving this general problem. Okay, and the main goal there is to try to explore the properties of function. For example, the smoothness, the strongly convex, and also the structure of the objective function to reduce the iteration complexity. Okay. In the third part, I will talk about randomization approach. So because many machine learning data mining problems are formulated based on a data matrix X, so if the X is very large, so computation cost is very high. So here we're going to talk about the randomized approach that tries to reduce the size of X. Okay? So first we obtain a smaller sketch, and then we define algorithms based on smaller sketch. And we hope that the model we obtained from the smaller sketch is very close to the model we obtained from the original data X. So there I will talk about randomized classification, randomized regression, and also some other tasks, for example, randomized singular value decomposition, randomized k-means, so and also randomized kernel methods. So there, the main goal is try to explore utilize the properties of the data to try to reduce the size of the data. Okay, so please stay tuned. So next, I'm going to handle the control to my colleague Qihang, and he will talk about the optimization. And if you have any questions, you can ask now, or Qihang will continue.
Okay, thank you, Tianbao, for the introduction of all of these backgrounds for convex optimization. So I will talk about the optimization part, which will basically build upon the knowledge Tianbao introduced. But I understand that because Tianbao goes through this quickly, so if you miss any definitions and want me to clarify, please feel free to stop me. I will tell you the definitions, and it help you to understand my part. So here's the outline of my part in this tutorial. So first of all, I would like to introduce gradient or subgradient method. So this part, I will focus on the deterministic optimization. I'm not going to spend too much time in this part because this tutorial is mostly about the stochastic and randomization methods. But it will give you some basic knowledge about first order optimization, which will help you to understand the rest of the part. So in the other part of this tutorial, I will talk about the stochastic methods. I will focus on two parts. First, I will talk about the stochastic optimizations if you have in a single machine settings, in the case where you are able to put all the data in one machine and run your analysis. In the second part, I will talk about the case where data is too large to be stored in one machine, so they have to consider distributed optimization with data stored in different machines in a cluster. So again, let me remind you the models we consider. This model, although it doesn't cover all, but I think it covers most of the machine learning problems, including regression and classifications. So here, xi is the data points. Xi is the data points, yi is the label or response, right? And we only focus on the linear model. W is the parameter. W transpose X is the prediction linear model. And the L measure the discrepancy between what you predict and what is the true answer in your data. And we calculate this and call this as a loss. We don't care the loss on one single values, we care the loss on average. So that's why we sum them divided by n. Small n is the size of the data, and RW is the regularization term, which can help you to fix this overfitting problem. So in optimization, we call the whole thing here objective function, denoted by capital FW. So first of all, most of optimization methods are iterative methods. It means that it has to take several similar actions made for many steps iteratively until the solution converge to the best parameter for your models. So because these iterative methods, first thing we want to understand is how many iterations we need to run the algorithm before we stop, so that we end up with a reasonably good parameter, so that we can use this parameter to build a model to do prediction. So how do we measure the goodness of the parameters? There are many different ways, but if you agree that if you minimize this optimization problem and you solve the models, this model will be very good as a predictor, then you would like to actually really solve this problem to optimality. So we want to actually find W such that it reaches the smallest value of this capital F. So usually, if you look at this picture, that's what you can typically observe when you run the optimization algorithm. Horizontal line is the number of iteration, and the vertical line is the objective value, the value of FW, and W is the current solution, intermediate solutions. So usually it decreases nicely. But and the red line here is the objective, the optimal value, the minimum value of f, and the blue curve is the objective value during the algorithm. So now we would like to introduce an important concept called iteration complexity. So iteration complexity, suppose in the middle of the algorithm, you have already run your algorithm for capital T iterations. You end up with a solution W hat T, and you evaluate the current solution. Now, what is iteration complexities? It tells you how many iterations you need in order to make sure the current objective value is at most epsilon away from optimality. So if you look at this picture, the optimal one is this red line, and the current value after, for example, 80 iteration is this value is pointing here on this blue line, and the difference between the blue line and the red line is epsilon. You are still this much away from optimality. So it really depends on how much computational budget you have, or how much time you want to spend in solving these optimization problems, or also depends on your tolerance to these epsilons. So you may determine how many iterations you need to run, right? Suppose you are satisfied with a large epsilon, you just run a few iterations, you get a solution quickly. If you're really specific about the epsilon, you want this epsilon to be very small, you get a very high precision, and usually you will need to run many iterations. Now, there's always a trade-off between the time you spend and also the quality of the outputs, right? Now, in most of this talk, I would like just basically to show you this trade-off. How is the number of iterations depends on your targeted epsilon. And there is a related concept called convergence rate. It's nothing new. It's very similar to iteration complexity. You can obtain one from each other. So the difference is that in convergence rate, we state this thing in a little bit different way. It means that convergence rate means after t iterations, what is the distance from your current objective value to optimal objective value? So you can see when we talk about iteration complexity, we set out targeted epsilon, and this complexity tells you how many steps you need. When we talk about convergence rate, we give the iteration first. You say, I want to run 100 steps. Now, the convergence rate tells you, oh, this will be your expected epsilon. So it depends which one you fix first, and you talk about the other. So any questions so far? Yes?
So usually what you would like to is more to have a good, so you would like to optimize not really your loss on your training data, but you would like to basically your model to work well on test data.
Yes.
And actually there is a dependence here because maybe the minimum point that you will find here will not be the best one.
Exactly. So actually, so there are two things. First of all, you don't know what kind of a precision you need to guarantee, right? If you just solve this problem with a very large epsilons, of course that's a very bad generalization error, right? According to all existing theoretical results, it doesn't really give you a clear answer. If you have this many data, this many features, it's enough to stop there. So I think the safest way is still run the algorithm with ending up with a small enough epsilon, right?
Yeah, I remarked to that. So here we are in the big data workshop, so I can ask a question. Usually when you are in a small machine, what you can easily do is to tune your parameter on the test data. That's usually what you do when you do some kind of cross-validation.
Right.
And I guess that I would like to do that on a big scale too.
Right.
So the question is, okay, this is a question maybe at the end of the talk I would like to have is it doable or not?
So you want to optimize the tuning parameter as a part of the optimization process. Is that what you want to do?
Yeah, I want to optimize it
So
at a big scale, but still using.
yeah, the thing is that if you want to optimize the tuning parameter as a part of optimization, the thing is that first of all, the optimization model is not clear. What is your loss function? So if you include a lambda as a regularization. And second, it's non-convex. It has a lambda w, right? It's not just w. And actually, what I think the best thing to do is to give you a very efficient algorithm that can minimize the models for a particular tuning parameter, such that it becomes more efficient when you change the tuning parameter. If you try one value for tuning parameters, it takes you several days, and you realize, oh, it's not a good tuning parameter, and change to another one, and it wastes already several days. So if the algorithm, optimization algorithm is efficient enough, it actually helps you to choose the tuning parameter as a subroutine. And of course, when we say the optimization is good enough, I assume it should be scalable for large data situation. Okay. Okay, so here we have two concepts which are basically equivalent to each other, but I will focus on the first one, the iteration complexity. So when we talk about the overall efficiency of the algorithm, we use the runtime. So what's the runtime for your algorithm? So iteration complexity measures how many steps, but what we care more is how many seconds we need to run this algorithm, right? So runtime is actually the per iteration cost in time, how many seconds you need to run each iteration, multiply the total number of iterations you need. Of course, it depends on epsilon, right? So here, I want to introduce a few possible iteration complexity or convergence rate we are going to encounter today during the tutorial. There are basically two big classes of convergence rate or complexities. First one is called a linear rate. If the distance for current solution to the optimal solution reduced to 0 in this kind of way, mu is something less than 1, t is a number of iteration. If the convergence rate like this, then it's called linear, right? If your algorithm has this property, it's very nice. Usually it converges to a good solution very fast. However, in the second case, it's much worse. It's called sublinear. Your objective value converges to optimality in rate 1 over t alpha. Here, alpha is a positive number. So this one still converges to 0 as t goes to infinity, as you can see, but it's much slower than exponential convergence rate or linear convergence rate. And here are the equivalent iterative complexity for linear and sublinear. If you are lucky, you are in the sublinear cases, the algorithm can guarantee the epsilon solution in log 1 over epsilon iterations. So if you take a log on something, it's not going to be very big, right? However, if you're unlucky, you have a sublinear algorithm. You have 1 over epsilon, 1 over alpha. The alpha is the same alpha here, so they are equivalent. So in this case, it's less desirable because it may increase faster when epsilon converges to 0. You may need to run more iterations for a very small epsilon compared to the linear case. Okay, now why we are interested in these bounds, just as I mentioned, first of all, you need to know how many times you expect to run this algorithm, and you need to decide whether it's worth to do that. Okay, second, after I introduce several algorithms in the talk, they will have different properties on different classes of the problem. So there's no universally good algorithms. So when you choose the right learning algorithm for your problem, you may need to look at their convergence rate. And it really depends on the problem. So you want to pick the one actually according to the criterion, either convergence rate or iteration complexities, such that it gives you the best performance. So here there are, if you are lucky enough, you have a linear convergence rate with a mu equals to 0.5. T is a capital T is the number of iterations. If you want to get epsilon like this small, you may only need a few seconds. However, if you have 1 over t, which is a sublinear convergence rate, and you can see the green curve is here. It still converges to 0 when the iteration number goes to infinity. However, it's slower. It's on top of the blue curve. So if you want to get the same epsilon as you get in the linear case, the sublinear case will require many more iterations. It will be like maybe a few minutes. And if you are even worse case is that when you have a sublinear convergence rate with a very small alpha, like a 0.5, less than 1, then in this case, it still converges to optimalities. However, it takes more time. You may expect a few hours. So you can see, although there are two classes, linear and sublinear, there are somehow kind of subclasses within these classes. Some are good sublinears, some are bad sublinears. Of course, in the linear cases, there are other categories. Some have super good linear convergence rate, reasonably good linear conversion rate, and something like that. Okay. So here, let me order all kinds of the convergence rate or complexity we may need during the talk. So the best one are on the left, the worst one are on the right. So anything like this will be good. If you have a dependency like 1 over epsilon to any polynomials, then that would be very bad. Okay. So after I introduce all of these complexities, you may ask, what kind of properties of the problem that eventually determines the convergence rate of the algorithm? There are two important properties, which one is the smoothness, and second one is strong complexity. So smoothness actually is related to what kind of a loss function you use for your problem, right? For regression task or classification task, these two loss functions are non-smooth. For example, the loss function SVM is not smooth. And if you have an absolute loss function in regression, it's not also non-smooth. So if you have a problem with this kind of a loss function, it's going to be more challenging in an optimization perspective. The algorithm is usually slow. You may have a sublinear convergence rate. However, if the loss function is really smooth, for example, square hinge loss, logistic loss, or square loss, then this optimization problem is relatively easier to solve. So it's more scalable for big data optimization because it converges faster. And also, another thing is that you may want to think about if you really want to use non-smooth function, given that the smooth function helps you to help an algorithm converge faster. If the performance, prediction performance of the, for example, quadratic hinge loss is not that much different from the hinge loss in SVM, you may want to just use quadratic hinge loss. It has some better property in optimization. Then let's talk about the strong convexities. As Tianbao introduced, if the problem is, or the function is strongly convex, it means that you not only have a lower bound, you actually have a quadratic lower bound, okay? So here, this function, the Euclidean non-square, is actually strongly convex. We actually call it lambda strongly convex. This lambda refers to the same lambda here. It's actually the strong convexity parameter. And also, if elastinat is also strongly convex. So when we talk about strongly convexities, we don't care about the smoothness in the regularization term. You can see, technically speaking, this regularization term is non-smooth because of this one node. There's a kink point. However, we don't care. We only care strong smoothness when we talk about the loss function. But when we talk about strong convexities, we only refer to the regularization term of W. So if you have a strongly convexity in the regularization term, the problem is relatively easier to solve. Otherwise, it's harder. And you can see these two functions are not strongly convex. In the case you don't have any regularization or you have only one node, then these problems are relatively harder to solve than a strongly convexity one. Okay, so here is the first algorithm I will talk about today. It's very simple. It's called hill climbing. It's just the gradient method. So you calculate gradient and go along this direction with a certain step length. And because it's gradient, it guarantees that you can go to the lowest point of the function efficiently. That's the intuition. So we know, let's talk about deterministic method, which means you have to use all the data without any sampling, because sampling introduced stochastics. So here we calculate the gradient of the first part and the second part. This is the gradient for the second part, this is the gradient for the first part. Because the function is the average of the loss, the gradient is the average of the gradient of the loss. So that's why you have this form. You can see to calculate this expression, it takes ND complexity because D is the feature and is the data point. You have to go through every feature of every data in order to evaluate this. So it's very time consuming, right? And however, if you are able to calculate it, for example, the data does not have too much features or the size is small, you can calculate it efficiently. So this is exactly the hill climbing step. Okay. So now when lambda is 0, which basically means this term disappear, you only have this term, you don't regularize the problems, then as I said, this problem becomes non-strongly convex, right? Remember we said this is a challenging case to solve. Indeed, if you run the deterministic gradient methods, we know you need 1 over epsilon iterations. Remember, this is so-called a sublinear rate, and we call it a bad situation because it's slow. That's exactly because you don't have a regularization. And second, if you have regularization, lambda is greater than 0, and you have 2 known here, then the complexity becomes very different. 1 over lambda log 1 over epsilon. And this will save you a lot of iteration because it's log 1 over epsilon. But there's a dependency of lambda, 1 over lambda here. So this lambda is a tuning parameter you want to do when you do cross-validations. Of course, it depends on what kind of out-sample performance, but in terms of optimization point of view, the smaller lambda give you a harder problem to solve because small lambda make this problem close to non-strongly convex problem. If lambda is large, this problem becomes more strongly convex and it's easier to solve. That's why we have a dependency in terms of in this kind of reciprocal form of lambda, 1 over lambda. Okay, so actually this is not the best deterministic algorithm. You can do something better, and people in optimization community has already studied this very well. So this is sort of acceleration scheme. The idea is that let's not just keep a W and go along the gradient of the W steps. What we do is that we keep another auxiliary sequence called a V. Right. What we do is that we stand on V, we calculate gradient on V, and we do this hill climbing steps along the gradient. We go to a new point called W. We don't start to calculate a new gradient on W and go another step, gradient step again. What we do is that we look at our trajectory. we look at what's the difference between this W and the last W. And this is so-called momentum step. It tells you how did you come here. It doesn't matter. It's not necessarily the gradient. It's just the difference between two consecutive solutions of W, right? And you want to go a little bit further along this momentum direction. And this momentum direction is a different direction from the gradient direction. So this algorithm basically uses both gradient and the momentum direction to update the solution. So if you go along the momentum direction on W, you end up with a new V, and you go back to calculate gradient on V. So using this auxiliary sequence and these momentum steps, this algorithm becomes faster. How fast it is? As follows. The blue or the red one is the previous result. The blue one is the accelerated one. If you use accelerated steps, but you don't have strong convexity, you get 1 over square root epsilon. It's still sublinear, but this is so-called not that bad sublinear, right? It's still slightly better than 1 over epsilon because there's a square root, right? If epsilon is 0.01, this term is 10, but this term is 100. So it's still different. However, if you have a strongly convexities, if you use accelerations again, you get log 1 over epsilon still. So it may not help too much compared to the previous log 1 over epsilon dependency. However, it's better in terms of the dependency on lambda. As I said, the regularization term lambda is close to 0. You need more iteration. But here, you take the square root. So it still saves you a few iterations, especially when the regularization term lambda is very small. So indeed, in many cases, lambda should be very small. It's like 0.001. And according to some statistical literature, lambda is chosen in the order of 1 over square root of data size. But of course, in practice, people do it with cross-validation. That bound is just theoretical bound. OK, so now you may have asked question, why do I focus on these nice regularization term? Can I include other regularizations? There's a yes. The answer is yes, but I will just give you a brief answers. I'm not going to show too much details. So suppose you have another term, like a non-smooth term, one known of W. And as I said, if you have a one known, it means this R is non-smooth, right? But it can still be strongly convex. What we do is that I separate this W one known out of this other part of the regularization, for example, two knowns. And we assume this R primes is strongly convex and smooth, so that I can merge the smooth term together, then I can calculate its gradient. And how do we handle this non-smooth term? What we do is the following. So this is so-called accelerated proximal gradient step, actually. Instead of just go along this, using this hill climbing steps, we don't use the gradient in that way. We use the gradient of a small part to calculate, to construct this sub-problem, which is a quadratic minimization problem with W1 norm here. So you solve these problems with the gradient defined on the sequence V, and you obtain a W, and you still do the regular momentum step. So this is the difference. We don't do this simple gradient step. We have to solve this sub-problem. And you don't need to use another optimization tool pack to solve this minimization algorithm. It has a closed form. You can write it down in the paper and implement it in your code. So this closed form is called a soft stress holding, by the way. And all the complexity and the runtime I mentioned before doesn't change. Everything remains the same. Okay? So because of L1 norm doesn't really affect our complexity, the main results. In the rest of the talk, I will mostly focus on the two known cases. So that we don't need to worry about this proximal gradient. So now let's look at subgradient method. As Tianbao introduced, you have to use subgradient if your problem is non-smooth, because there's no gradient available to you, right? And we can do is the following. So we can calculate subgradient using all data, and this is so-called subgradient of the function, right? And we just replace the gradient notation to subgradient notation. You can still run this hill climbing steps, just like we would do for regular gradient steps. Very similar. And but the non-smoothness actually change the complexities, number of iterations dramatically. So if the problem is non-smooth and non-strongly convex, you have no good property to rely on. So the logarithm becomes very slow, and the complexity is 1 over epsilon squared. And this is an extremely bad sublinear case, right? Remember, original one is 1 over square root of epsilon when you have a strong convexity, when you have a smoothness. Now, since it's a little bit better in a strongly convexity case, but if the problem is still non-smooth, you don't have a linear convergence rate, as we said. previously we have a log 1 over epsilon. Now the best you can expect is only 1 over epsilon over lambda. So regularization term is still playing a role here in terms of the smaller regularization give you more iterations, but the dependency on epsilon is only 1 over epsilon. So the conclusion is that if a problem is really non-smooth, if you use stochastic gradient, stochastic subgradients, you can never get linear convergence rate. But you can get a linear convergence rate if you use other algorithms I will talk about. Okay? And we mentioned this, there's a general acceleration scheme using this auxiliary sequence and momentum step, right? But that only works for deterministic method. It cannot be applied here. So there's no blue and the red convergence rate. There's only red, bad convergence rate. Okay, so here is the summary of the deterministic methods in the tables. The conclusion is that if you have a strong complexity, if you have a better complexity, you have fewer iterations. If you have a smoothness, you have a fewer iterations. If you have both of them, it's the ideal case, it's so-called linear convergence rate. Otherwise, you only have a sublinear. Now, what's the problem for people to not to use deterministic method? Of course, it's because the scalability issue. Because deterministic method require you to use every feature of every data point during each iterate. That's too much if the either data size or dimension are huge, right? That's why we need to introduce stochastic methods. So there are 5 different stochastic methods. Stochastic gradient step, stochastic variance reduced gradient, stochastic average gradients, and also stochastic dual coordinate ascent, and accelerated proximal coordinate gradient. So I will assume all the data has been normalized such that the norm of each data is less than 1, just to avoid some dependency of the complexity on the norm of the data. Okay. So this is actually the most widely used optimization community in like deep learning problems. The reason I don't know why, but I guess it's because it's very scalable. And the good thing is that you can apply it to non-convex problems, and deep learning is actually non-convex. Okay, but I will still focus on the convex cases because in convex cases you can say more about the complexity, iteration complexity. Okay, so here's the full gradient. What we do is that get rid of this summation, so that we don't need to run over all the data. What we do is just sample one data I, calculate the gradient for this I data I. You can see I only have one term here instead of n terms. But I don't change the gradient for the regularization term. It's easy to calculate anyway. A good thing about this is that if you guarantee every data has an equal chance to be sampled, this gradient, expectation of this stochastic gradient is the gradient of the original problem. So it's so-called unbiased estimator, right? So now here is the algorithm of stochastic gradient. Still, it's very intuitive. Sample a data, calculate a stochastic gradient. This is stochastic gradient for both loss term and the regularization term, by the way. So you calculate them and go along these directions. But the difference is that when you use stochastic gradient, usually you have to average the historical solution. It's not the last one. Although some people, they talk about that it's good to use the last one, but in practice, it's usually to average them in order to reduce some noise. Like the problem in the stochastic gradient is that every time you get a direction, it might not be the optimal direction. It sometimes gives you the opposite direction. It makes the objective value even higher. So if you plot the curve, you can see a lot of noise. But if you take the average, this noise will be canceled out a little bit, right? So this is a very easy to understand. It's still hill climbing, but you use a noisy gradient, noisy direction. So here is the complexities. If the problem is non-strongly convex, 1 over epsilon, let's say as a subgradient descent. If the problem is strongly convex, 1 over lambda epsilon, still the same as a subgradient descent. In this case, if you use stochastic gradient descent, you get exactly the same result as subgradient descent. There's not much difference. Okay? And we want to worry about the per iteration cost. If you use subgradient descent, we know the per iteration cost is ND, but now if you use a sampling, it's only D because you use one data at a time, right? And for example, if you use hinge laws, the subgradient for hinge laws is given like this. It's just if language, right? Calculate the inner product and run the if language, you get a gradient. And the cost OD is paid to calculate this inner product here. So it's OD. Okay, so the table is the same as you see before because the complexity, iteration complexity of subgradient is the same as a stochastic gradient descent. All right, but the difference is that we reduce the per iteration cost. Okay, and in this case, from these tables, you can see if you compare the first row and the second row, it's different. But if you compare the first column and the second columns, they are not much different. the conclusion is that strong convexity helps you to improve the stochastic gradients complexity, but the smoothness doesn't matter, right? So it doesn't matter if you use hinge loss or square hinge loss. The iterative complexity is the same. What matters is whether the regularization parameter lambda is 0 or something positive. Okay, this is the conclusion for stochastic gradient, but it's not true for other algorithms. And let's make a small comparison about the deterministic method and the stochastic method. First of all, full gradient method usually need fewer iterations to converge, but stochastic gradient need more. But the good thing is that stochastic gradient has a lower prediction cost. Now, if you really want a very small epsilon and the data is not that large, you want to use a full gradient method for sure. However, if you are satisfied with a relatively large optimization error, just like someone says you have a generalization error to worry about anyway, so it doesn't matter if you solve the optimization problem to to extreme optimality, then you can give a large epsilon. In that case, you can use stochastic gradient. And the full gradients can be accelerated, stochastic gradient cannot. And the full gradient iteration complexity depends on both smoothness and a strong convexity, but a stochastic gradient only cares strong convexity, it doesn't care smoothness. Okay, and the previous table, we can see all the rates are sublinear. You cannot see log 1 epsilon in any cells here, right? Can we get any chance, is there any chance we can still get a run over epsilon using stochastic gradient? The answer is yes. That's a very new technique invented just 1 year ago. It's called SVRG. Stochastic variance reduced gradient. Just as the name suggested, the idea is to reduce this noise or the variance of this stochastic gradient due to data sampling. Okay, and unfortunately, these techniques only works when the problem is both smooth, with a smooth loss, like a square hinge, and the problem is strongly convex. For example, lambda is greater than 0. Okay, so here is the original stochastic gradient, if you remember. It's only defined on one data point. It's unbiased. However, the bad news is that its variance is even non-zero when you are at an optimal solution. For example, if you run stochastic gradient, regular stochastic gradient, I give you an initial solution that is already optimal. You run it, and you go away from optimality. You go to somewhere else. However, the good thing about this variance-reduced gradient is that its variance decreases to 0 as you're getting closer and closer to optimality. If I give you the optimal solutions as an initial solution, the algorithm doesn't change the solution at all. Even you sample the data, right? That's the very very good property. So the idea is the following. Let's use full gradient at a point called a W tilde, the so-called reference point, and they calculate this full gradient using all data on this reference point. But I only do this not very frequently, otherwise the algorithm is not efficient, of course. So what I do is that I construct the variance-reduced gradient using this reference points full gradient. And you can see this term. What is this term? This term is the regular stochastic gradient defined on data IT that is sampled. And this term is so-called a variance-reducing term. It's also a correcting term. It helps you to reduce the gradient of this vector, G tilde. And G tilde is our variance-reduced gradient. First of all, G tilde has the same unbiased property as the stochastic gradient. That's good property, right? Second, as I said, its variance really reduced to 0 as long as the solution, W, and the reference points converge to optimality. So we don't just use one reference point, W. Actually, in this algorithm, this reference point is updated less frequently, but still updated, so that both of these solutions converge to optimality. So I'll skip the details why the variance converges to 0, just give you the main algorithm. So this SVRG is actually a little more complicated. It's a so-called inner loop, outer loop optimization. In the outer loop, in each outer loop, they calculate a reference point called W's tilde S. Okay, and they calculate this variance-reduced gradient using the full gradient at tilde S. And we know this gradient has a nicer property than the regular stochastic gradient, and we run this step. This is exactly the hill climbing step, but we use the variance-reduced one, not the original one. We still need to average the historical solution, but once we do this, we get the average solution. This will be used as the new reference point. So you can see the inner iteration is k. We update the reference point after every k inner iteration, and the outer iteration number is t. Okay, how many k we need? K is usually chosen as 1 over lambda. And you can see there's a lambda. If lambda is 0, You cannot even define k. That's one of the reasons you cannot use SVRG when you don't have a regularization term. Okay, so here it will be the results. And now let's talk about the nice thing about this property. It helps reduce the noise, so it does achieve log 1 over epsilon complexity. So this is better than the standard stochastic gradient, which is 1 over epsilon instead of log 1 over epsilon, right? And the per iteration cost is this much. If you multiply them together, this will give you the total runtime, okay? And if you have L1 long regularizations, you can use this proximal steps to include this L1 long, just as I introduced for the deterministic gradient part. So I will not show the details again. Of course, we introduced this D on the runtime, which is maybe not desirable. However, at least we improve the dependency on epsilon. It's now log 1 over epsilon. Okay. And what is the second algorithm is called? Oh, before I continue, is any question about SVRG? This variance reduce technique. Yes?
So you're assuming for the last 10 minutes that step size is somehow be optimized with cross validation?
Oh, I didn't put too much details on step size selections. Usually, I have to say, in practice, you have to really tune the optimization, the step size for optimization. It's one of the tuning parameter. You are right.
So even for the SVRG, it's choosing is as bad as SGD?
No, that's a good question. For SGD, it's harder to tune because the step size change with the number of iteration is usually decreasing. But for SVRG, it's constant. Sorry, I didn't show this important information. When you use stochastic gradient, the step length is usually 1 over square root t or 1 over t. T is the number of iteration. So you want to go to a shorter step and as the iteration converge. But for SVRG, it's actually always a constant. But you still need to tune that constant. But what we know is that you don't have to make it depend on the number of iteration. Yeah. Yes?
When you tune it, you need to, like, does that make sense to tune it by cross-validating on a smaller sample? Or?
No, I don't. So when we do cross-validation, we worry about the generalization error. We want to see how it's performed on the holdout sample, right? But when we do optimization, we worry about the efficiency. So the best way to tune the parameter is to run a few iterations using this parameter, compare different parameters to see what a reduction in the objective value. Choose the step length that gives you the biggest reduction. Yeah. But the general rule is that you want to make it 1 over square root epsilon, and you multiply a constant in front of 1 over, 1 over square root t, and you multiply a small constant in front of this square root t. You only tune the constant. Don't tune the square root t. Usually it's 1 over square root t. That's for stochastic gradient. So you just run a few iterations to see which one gives you the most reduction, and you use that step length.
Isn't it possible that you're going to have a parameter that's going to give you a better value even though it wasn't as good at the start?
You mean,
Like something that's going to go lower in the optimization value because it had the decrease rate was lower at the start and then it goes much lower than all the others? Is it possible? That actually you make a mistake by choosing the best one on a few iterations, but actually the ones that you rolled out were actually better for in the longer run. Is that possible? Or is it something?
is it possible? It's a good question. It's possible. So it's good that the step length might be bad at the beginnings, but it might be good in the end. But I think it's still open question. So far as I know, it's either just tuning manually or there is something called adaptive step length algorithms. And you can run that algorithm. They can automatically search the step length for you. But the idea is like what we said. Just the algorithm basically also, the step length tuning algorithm also use the same idea as I told you to look at the reduction in the objective value and search the solution. Sometimes people use restarting technique that can also help you to search the step length. But in general, there's no good way to do that automatically, I have to say. Yeah. OK. So let's talk about SAGA, Saga. So there's actually a new paper, called an older paper called SAG, which is earlier version of Saga. If you look at the papers, the convergence analysis is very complicated. And what Saga does is that introduce a little bit change the updating rule a little bit so that the convergence proof is reduced from like 10 pages to 2 pages. So it's basically a theoretical improvement. Oh, sorry, the technical improvement. The complexity of SAGA and SAG are essentially the same. So I will focus on SAGA. So now this is more applicable than SVRG. Now you can apply it to non-strongly convexity problem. This algorithm only asks for smoothness. It does not ask for strong convexity. So let's make it a little bit better. So here is the ideal. So SAGAs is also another technique that can reduce the variance of the stochastic gradient, but it's different from SVRG. So here, if you look at this part, this is exactly the SVRG. We need a reference points. Okay, we need a reference point and calculate the full gradient at a reference point. Okay, now let's remind you the formula for the full gradient at a reference point. If you look at this term, within this sigma summations, this gradient is evaluated at the say reference point W tilde. The idea of Saga is that they use a different W for different term in this summation. Basically for different data because this summation is over each data point. So you can see here, they have a W1 tilde, W2 tilde, Wn tilde. Basically each data have a different Wi tilde. So that's the difference. And if you look at the gradient step, it's calculated in the same way. They need a regular stochastic gradient and variance reducing correcting term. The difference is that this one uses this full gradient at reference point, and this one uses the gradient of the loss function at different solution point. And that's why they call it Saga average gradient, because G is by definition an average of this gradient. Okay, so yeah, here is a little bit technical. So what we do is, what this algorithm do is that it chooses initial points and calculate the gradient of the loss function at every data points. It's very standard, it's just averaging length. So essentially, the initial average gradient is still calculated on the say solution. However, during the algorithm, once you get a new solution and a data samples, you replace the gradient corresponding to this data sample in the formula of this average gradient. For example, you get IT, it deducts the IT and add a new stochastic gradient here. So that actually when you have to update the average gradient in a more complicated way because each term here is evaluated on different solution. And once you calculate the stochastic variance reduced gradient, you can still go along these gradient steps. So the idea is still go along this variance reduced gradient, but it's updating in a much more complicated way. So if you look at the difference between two consecutive average gradient, they only differ in one term, GI. I corresponds to the data you sampled. So what we do, you don't have to calculate each G again and take the average because only one term is changed. You can just deduct the old term, add the new term. However, before you sample the data, you really don't know which term you need to remove. So that's the bad things. During the algorithm, unfortunately, you have to maintain each G, G1 to Gn, and see what is the next data. If the next data is 2, okay, you deduct the G2 and add a new G2. However, for other algorithms like SVRG, it doesn't need to store all GI in the memory. It's enough to store their average as a single vector. Here, you need really n vectors. So that's actually a drawback of Saga. Although the per iteration cost is OD, as low as the SVRG and the stochastic gradient. However, it requires ON extra memory space in order to store all of these vectors that give you the average gradient. You cannot miss any of these, otherwise this algorithm cannot be applied. But I think ND is not bad because exactly the data size, right? As long as you can store two data set, which is so as long as you can store another data set, which is exactly the same as your current data set, then you can afford to run this Saga algorithm. It's not really a big requirement as far as I know. So here is the complexity results. Still, it cannot be applied if the problem is non-smooth. So if you have a hinge loss, you cannot use this algorithm. So it cannot be applied to SVN. But it actually can be applied when the problem is non-strongly convex. We have this cell fill in right now. Originally, it's still missing. Okay. Now here is the overall complexity. You need this many times per iteration, and this is the total iteration you need. Multiply it together. So this is a little bit interesting compared to the stochastic gradient methods. So n and lambda are now no longer multiplied together. It's actually separated. It's n plus 1 over lambda. If you remember the complexity for SVRG, they are exactly the same. So Saga have the same overall runtime as SVRG, but it's more applicable. Okay. So before I continue to talk about other techniques, so here let's stop a little bit just to summarize what the difference between the three algorithms we have already introduced so far: stochastic gradient, SVRG, and Saga. Right? If the problem is smooth, like a square hinge loss, but non-strongly convex, what you can do is you have two choices: SGD, Saga, SVRG is not applicable. So if you look at this complexity, you cannot say which one is better than the others overall. For small epsilons, Saga is better because it requires 1 over epsilon iteration. However, the other one requires 1 over epsilon square. But the good thing is that Saga, SGD does not have an n here, because they only sample one data at a time. But here, it really has an n here. For if you have a smooth and a strongly convex, story is still very similar. The only difference is that now you can use SVRG. But as I said, it doesn't give you any extra benefit in addition to Saga. So again, the story is that if you want a small epsilon, just do SVRG or Saga. The solution is very precise. However, if the data size is really large, and you are satisfied with the large epsilon, then you can use just a regular stochastic gradient. Okay, so let me see. Okay. So we are going to talk about another two algorithms which have some advantage compared to these three guys. So, but they belong to a different categories of algorithms. They are applied to dual problem rather than the original problem. I think you may have already heard of the dual problem before, but for this purpose of this talk, I would like to just briefly review what is a dual. So this is the loss function. Z is a W transpose X, so I just merge them into a one notation Z. And Yi is the label or the continuous output. It doesn't matter. But it depends on I, so this Li Z is the loss function for the I's data. Okay, so let's define the dual conjugate dualities. So this is so-called dual function denoted by Li star. It's a dual function, the conjugate function of Li. And the variable is alpha here. They are defined in this way. You can see the formula are exactly the same. If you give you a conjugate lambda star, you can calculate lambda. If I give a lambda, if you give you L, you can calculate its conjugate. If I give you a conjugate of L, you can recover the L using the same formula. So this definition can be applied to both the primal and the dual. So here I will give you just two examples. If you use hinge loss, so the conjugate of the hinge loss is essentially a truncated linear function. It's linear on some interval, but go to infinity outside the interval. If you have a square hinge loss L, and you calculate its conjugate using this formula, do some simple calculus, you can obtain the following. It's a piecewise quadratic. It is a quadratic function on an interval and go to infinity outside the interval. Okay? Okay, now we know there's a conjugate dualities defined for each loss function L. Then we can define a conjugate function for the whole problems. And actually, we want to use optimization problem to solve the dual rather than the primal problem. And the solution in the primal problem can be always recovered. So this is actually the most widely used algorithm in the popular tool pack, liblinear and libSVN. Okay, and it's called a stochastic dual coordinate ascent methods. And recently, it is also studied from different aspects in theory by Xiaovi, Schatz, and Zhang. And it's applied only when this regularization term RW is strongly convex. So, but it doesn't require the smoothness compared to SVRG. SVRG always needs smoothness, right? But now it only requires strong convexity. Smoothness is not required. So they have both pros and cons. They apply to different situations. So here is the derivation for the dual problem. This is the original problems. We treat this inner product as a Z, and we write down the definition for the conjugate dualities. It is defined as a maximization problem here with a variable alpha, and alpha is so-called dual variable. If you have n data point, you have n dual variable. If you have d features, you have a d primal variable. So number of primal variable corresponds to the features, and the number of dual variable corresponds to the data point. Each data point will receive a dual variable. It's just in R1, so you have a n dual variable. So here we have n alpha. Each alpha corresponds to a data points. And we write it down, switch this min and max. We are lucky because here we have a 2 known square, so that this minimization can be calculated in a closed form. So you replace in the closed forms, you end up with this quadratic kind of optimization problem. It's a maximization problem. But don't worry, because its power is concave. It's good to minimize convex function. It's also good to maximize the concave function, so the problem is still tractable. So here is the dual problem so we just obtained. It's in terms of the dual variable alpha, so it's now in Rn instead of in Rd. What we do is the following. We randomly sample a data point, it, and we optimize the dual variable alpha it, only for this sampled data, right? So we still do sampling. We're sampling still over the data, but we are updating the dual variable, which is only R1, because this is just a scalar, right? So it is hard to just minimize the problem in RIT directly because list term actually involve all data. If you want to evaluate list term, it's already very costly, it's ND. So we don't want to do that. What we do is that we introduce a primal solution, WT, that is defined as a list parameter, a dual parameter alpha IT, multiply each vector, and sum them up. So now, using this primal solution, you can do some changing of a variable. Instead of doing optimize over alpha I, we optimize over the change in alpha I. So you can see this is always equivalent. Instead of tell you what's the best solution, I'll tell you what's the difference between the best solution and the current solution. It's equivalent. So what we do is that we now introduce this changing variables, the delta alpha I, and we rewrite the problems. And because we introduce the primal solution in this way, you can see this problem is now reduced like this. Compared to the original formula, the nice thing is that we don't have to worry about, we don't have to go through every data. We just need to focus on the delta alpha t. And we solve these problems in closed form in many cases. So here is the delta AIT defined on the dual problems, only on the parameter alpha t, alpha IT. And we update the new alpha according to what we solve, the delta alpha. And we need to also update the primal solution WT using the new the change of the dual variable. This update actually preserves this formula because alpha is here. If you have a delta alpha, you only need to plus delta alpha multiply the corresponding term xt without going through the whole data set. If you evaluate this one, will require you NT complexity, but you only do it in the first iteration. In the other iteration, you only need to add one data point with multiplied by this delta alpha. The type complexity for this one is only OD. Okay, so this is still has a low per iteration cost. And this optimization problem actually has a closed form. So you can actually look at this paper to find out the closed form for different lambda. They have a closed form for hinge laws, for SVM, square hinge laws, and logistic regression. But for logistic regression, it's different, sorry. So it has closed forms. For example, for square laws, for example, L is square loss in a regression case, and the L star is the conjugate, and this problem allows the following closed form to update alpha. You can see what you need to do is the most costly step is to calculate this inner product. These two known, you don't need to worry about them because I assume everyone is every data is normal is already normalized. If not, you can calculate their norm at the beginning. You don't have to calculate it in every step. So this one is still only big OD complexities. However, if you apply this to logistic regressions, there's no closed form, unfortunately. But in their papers, they actually suggest a nice way to approximate the solution. So it's still very costly. It's still very time efficient. It's still OD using the approximation scheme. So here's the summary for SDCA, stochastic dual coordinate ascent. You can see it's not always applicable. If your problem is non-strongly convex, then unfortunately you cannot use that. So this method basically requires regularization term. However, the good thing is that it doesn't matter the problem is smooth or non-smooth in this sense. So, but the complexity depends on the smoothness. Okay? So in a non-smooth case, we know it's harder to solve, so we can expect the complexity is worse, 1 over epsilon lambda plus n. And the other one is better. We have a linear convergence rate log 1 over epsilon. So in order to compare this method to other methods, we have to focus on the best case, smooth plus strong complexity, so that everyone can be applied. That's why we can compare them. So if you compare with this SDCA with SVRG and Saga, the conclusion is that the overall type complexity is the same. So there's no really any difference. Of course, they can apply to different settings depending on smooth and non-strongly complexity. But if the problem is both smooth and strongly convex, it doesn't matter which algorithm you use in terms of theoretical complexity. Some papers also compare their performance in practice, but sometimes one is better than the others. There's no uniformly best solution. Okay, here is the numerical result given by Zhang when he, in his SVRG paper. Here they compare SDCA, SVRG, and a stochastic gradient descent. They actually consider two different gradient descent. First, they choose the step length, as people ask, to be 0.01. They just use this step length, multiply 1 over square root t for the whole algorithm. The second one is the case they tune the step length parameter so that it performs best. So there are 4 curves here. The orange one and the purple ones are, these two are for stochastic gradient. So you can see if you tune the step length, of course, it converge faster. The horizontal line is how many data points you use, which corresponds to how many iterations, because you use one data in every iteration anyway. So you can see tuning step length helps to improve the performance of stochastic gradient. But for SVRG and SDCA, there are fewer parameters to choose. For SDCA, there's no tuning parameter at all. You don't need to worry about that. But for SVRG, there is a tuning parameters. So they also tune the tuning parameter for SVRG. But you can see these two methods, the SVRG and SDCA, perform much better than stochastic gradient descent. The reason is exactly consistent. The result is exactly consistent with the theory. So if you have both strongly convex and a smoothness, these two methods is log 1 over epsilon iterations. However, for SVRG, recall that it's 1 over epsilon, right? And this advantage actually becomes smaller and smaller if you make lambda closer to 0. So here it's for a smaller lambda. So you can see the SVRG and the stochastic gradients has a similar performance because the problem is losing strong convexity because lambda is too small. But for lambda is big, you can see there is significant difference. Okay. Well, now the last algorithm I would like to mention is the APCG. So APCG is basically the accelerated version of this SDCA. SDCA is a coordinate ascent. APCG is accelerated coordinate ascent, basically. So it actually, of course, should perform better. But the algorithm is more sophisticated in terms of the updating sequence. Remember, I mentioned there's the acceleration scheme for deterministic gradient method. Remember two things. First, the momentum steps. Second, another sequence. Rather than the solution W, we need to keep a V, remember? It's exactly the same techniques here. Instead of updating alpha, introduce a beta. So we solve the beta to get a new solution, but we don't use this new solution. Instead, we use this new solution to calculate a momentum step. So the current solution minus original solution, this is the momentum steps. It tells you where you were from. So, and we update the other solution beta. So I will skip the details of analysis, but I bring you directly to the final conclusions. This acceleration, of course, it helps. But how it helps? Here, remember, originally it's 1 over lambda. Now it's a square root 1 over lambda. So it helps when the lambda is really small. If lambda is very close to zeros, if you use APCG rather than SDCA, you have a better dependency on lambda. You need fewer iterations. Okay. So if you compare to SDCA and APCG, actually, this algorithm, APCG, works better when lambda is very small. However, it does still require a positive lambda. You can be very small, but it still needs something positive. Okay? Otherwise, it cannot be applied, as you can see from this table. And it doesn't matter if you use hinge loss or square hinge loss. Smoothness is not a big deal here. So we apply this, compare the APCG to its non-accelerated version, SDCA, to the following 3 data sets. These are for or classification problem. So we use this square hinge loss as an example we want to minimize. So we plot the optimality gap and the number of the passes of the data, which is the same thing as iteration. So its conclusion is very similar. APCG corresponds to the red curve here. So red curve converge faster than the blue one, which is the SDCA. And the black curve is the full gradient descent, the very first algorithm I introduced in the tutorial. So you can see the blue one is, the red one is better because it's accelerated version. But its advantage becomes smaller and smaller if you look from the first row to the last row. The reason is that in the last row, the parameter lambda is very small. It's 10 raised to -7. And here it's 10 raised to 5. So you can see as lambda converge to become something small, actually APCG has more advantage because it has a better dependency on lambda. So if lambda is really big, it doesn't matter you use which one. But if lambda is very small, as long as it's still positive, I suggest you to use APCG. Okay, so so I would like to briefly mention this technique. Although APCG is applied to the dual problems, but you can actually apply it to the primal problem as well. You can apply it to the primal problem as well. But I think due to the limited amount of time, I would just briefly suggest how you can use that. The example I use is actually Lasso problem. I think people are more interested in these kind of problems. It's a regression problem with a two-norm and a two-norm regularization plus one-norm regularization so that you can have a sparsity. And the idea is that calculate a full gradient, but don't use the every value in this full gradient. Only use the partial gradient, which is in the ith column or ith rows. Okay, and it's given by this formula. And update the solution only go along this partial gradient. You don't use the full gradient. You go along the partial gradient. And the good thing is that partial gradient is more easy to calculate. You don't have to calculate all d dimensions. You just need to calculate one dimensions. And it turns out that you can also include one norm using the proximal steps. And this partial gradient can be updated in ON complexity. So this is the proximal mapping step we introduced before. Let me skip the details, but bring you to the final answers. If you use the APCG for primal problem, you can still have a log 1 over epsilon dependency in epsilon in the best cases. But the good thing is that, but the difference between the primal application and dual application is that in the dual case, per iteration cost is OD, and the primal case, per iteration cost is ON. So it really depends on your data matrix is very thin or very wide. If it's very wide, it means you have more features than data, you use the primal version of APCG. If it's like this thin, you have more data than features, I think this is most cases, then you want to use the dual. That's why I focus on the dual cases in this talk. Okay, so here's the last picture about these single machine cases. I just want to mention in what cases you want to use which algorithm. So we basically classify the problem into 4 cases: non-smooth, non-strongly convex, smooth, strongly convex, and so on. So if the problem is very bad, you don't have any good structure, so the problem is non-smooth, like a non-strongly convex, for example. I don't know if that's a popular model. You have a SVM problem, but you don't use the two-norm regularization. Instead, you use one-norm regularization. I think people probably solve this problem somehow. But this problem is actually non-strongly convex and non-smooth. You have to use it as stochastic gradient. Other algorithm is neither applicable or give you a good solution, a better solution than SGD. Okay, then if the problem is smooth and non-strongly convex, like a regression problem without regularization, then you can use the Saga. If the problem is strongly convex but non-smooth, like SVM, you use the APCG. If you have both property, still use APCG. So, any questions so far? Yes?
So for ESTCA,
Yep.
number of parameters are including the number of data points you get?
Sorry, I couldn't hear you.
Just confirming that for STCA algorithm,
Yeah.
the number of parameters that you'll be optimizing,
Uh-huh.
will that be equal to the number of data points you have?
Exactly. That's dual variable. You are right.
For big data, if you've got a billion data points, you'll be optimizing a billion parameters.
That's right. Just like when you solve the dual of SVMs, so you have n data, you have n decision variable. So they are the same.
I didn't really get you. You were saying that you can't apply something on the distribution in the linear package. Sorry, I missed that.
Oh, for logistic regression, right?
Yeah, so you can't.
Yes. So you can still use that, but what I want to point out is that the solution you get, you don't have the closed form. So here is the SDCA. We want to solve these problems for each alpha. So this is essentially an R1 problem. I think it's a typo. It's not Rn, it's R1. But you still need a closed form. For square loss and a square hinge loss and hinge loss, you do have a closed form. But for logistic regression, you don't. So, but this paper they suggest approximation for the solution for this maximization problem. So it's not exactly the optimal solution for this problem, but it's a nice approximation. And
On the next slide, you've got, and that's the mean square error, right? So that's 1/100th of all.
this one?
Yeah.
This is square loss, for square loss only. This is just an example, the closed form for square loss. We don't minimize this. It's non-convex. It's a closed form. This is not minimization. It's just a closed form. You calculate it, evaluate it, not an optimization problem. So before we take a break, I think I still have some time to introduce. So I have some summary in these slides. This is easier for you to do some to look at for references. But I will skip these summaries. I will just look at a distributed method before we take the break. So. What we consider distribution is that if your data is too large to store in the memory of a single machine, you would like to use multiple machines to do the optimizations. But here, we face another challenging. First of all, it's like we have a low network bandwidth, such that the communications is a really time-consuming compared to everything in the single machine cases, right? And here is something basic some result about the communication trade-off, computation trade-off. If you have do every calculation in a single machines, and you can read the data in the memories usually in a scale of 100 nanoseconds. However, if you have to do the optimization over multiple machines, you have to transmit the data between different, transmit the solution between different machines. Then it's usually in this scale of a few hundred thousands nanoseconds. So the new challenge we face is actually not just the local running time, it's also the communication time. So I will talk about that later. So here we assume we have n data point. Now we have a capital N because it's the total size of the data is not a single data in a single machine. Capital N is the total size. We partition them in a disjoint way, partition them into a small data set, S1, S2 to Sm. Small m here is the number of the machine. Okay? So each machine receives one of these partitions, set in these partitions, okay? But it only access to its data. It does not have any information about the data in other machine. And we assume without lots of generalities, the data size in each machine is small n, which is a capital N divided by the number of the machine. But you can easily change that, introducing more technicalities in notation. So this is the global problem we want to solve. It's the same. The only difference is that I replace small m by capital N. Okay? So machine J actually solves the local problem. Let's define in the same way as the global problem, but it's only defined on small n, the data set this machine J has. So the summation is taken over J, I over Sj. So let's think about how do we solve this. Our goal is to solve this problem, not this one, right? How do we solve this problem? Eventually, we can get an optimal solution for the global problem. That's what we basically want to try to answer using distributed optimization. Let's think about the very naive techniques. I have 5 techniques in the previous part, right? Any algorithm, this is 5 different algorithms. Why don't we use any one of them? For example, stochastic gradient descent to the local problem. And each machine calculate a solution based on their own data using stochastic gradient descent. Now, machine 1 set W1, machine 2 W2, and machine 6 set W6. But we still need an answer for the global problem. So the naive way is to just take an average of the solution from each machine. Unfortunately, this does not converge to W star. No matter how many times you spend in each machine, no matter how many times you take the average. It never converges. So this idea doesn't work. Okay? But there is some interesting idea called a mini batch stochastic gradient. What we do is the following. We don't use each machine to calculate an optimal solution for their sub-problem. We just use each machine to evaluate a gradient from their own data. Suppose, so there's a center. Center send a WT minus 1 to every machine. Now, every machine is on the same page. They have the same W. And their job is to calculate the gradient using their local data. Each machine sample a data, S1 sample 1 data, calculate the gradient, G1. And this gradient is calculated at a same point. Right? S2 is calculating using a second data, calculate another great stochastic gradient, and so on. If you have M machine, you basically have M stochastic gradient. And we average the stochastic gradient rather than the solution. So this is different from this page. Here we average the solution. This is wrong. But if you average the gradient and use this gradient to update the solution W in the center, then this is a good strategy. Okay? So we know that if you have a few IID random variable, it's very noisy. If you take their average, they still give you the same mean, but the variance is reduced by square root of variance is reduced by n. Standard deviation is reduced by square root of n, right? this is exactly the idea here. If n machines, you have more data to sample parallel. You don't pay more time, parallel runtime, but you really reduce the noise in the stochastic gradients. Then you run these algorithms, you actually end up with a convergence guarantee. And this convergence guarantee is exactly the same convergence guarantees from stochastic gradient. Because if you look at the outer loop, it's exactly stochastic gradient. Okay, so, but as I mentioned at the beginnings, when we talk about distributed method, you cannot just look at how much time you pay in each machine, because communication time is sometimes dominating the local runtime. You run local algorithm for maybe 10 seconds, but your communication may take a few minutes. It can be possible if the network is really bad. So when we categorize, when we compare the simple machines, remember I only show you the table for runtime, and which is mostly about the iteration complexity. Now we want to introduce another concept called the rounds of communication. What's rounds of communications? It actually counts how many times this machine has to stop working and talk to each other and exchange message, right? And when they talk to each other, when they exchange message, they have to first establish connection, second, send us informations, right? That's really time consuming. So this is something we want to worry about. And of course, we should also worry about how much time each machine is running, because eventually it affects the total runtime you need to finish the whole task. So the formula of the total runtime is now like this. How many communication you need, like this, multiplies the time you spend between two consecutive communication. And this time consists of two parts. First part is the time they talk to each other. Second is the time they spend in doing their local communication, doing their own job. And you calculate the number of times they commute. So this will be the total runtime. So after break, I will introduce these algorithms and as long as also their rounds of communication. Thank you.